Hello friends, I am Deepak Balodi and welcome to the lecture number 6 of the very first module of electronic devices and circuits, that is semiconductor theory. And into this chapter we have seen the major carrier contributions, carrier concentrations and conductivity or conduction phenomena of intrinsic as well as extrinsic semiconductors. And now is the time to move for the problems and solutions, different various problems. So this whole lecture will be devoted to various problems, tricky problems, simple problems, and via different problems we'll try to cover as many as concepts possible. So for a single concept only one problem will be more than enough, but in different problems being covered here, you will definitely find some different concept or some tricky part, and most of the problems will be the problems which have already appeared into the gate examinations or some various important ISRO, BARC, BSNL examinations or in engineering services, as well as there will be some potential problems which may appear, or the similar problems may appear in some future examinations. So but what so far we have read, let me quickly brief it for you. That we have seen in this whole chapter that if we start with the intrinsic semiconductors, there is a band gap between this as known as Eg, which is Ec minus Ev. There is no absolute value for any energy level in the energy band diagram. There are only values as the reference, means we can only quote Ec minus Ev. For example, it is 1.1 electron volts for silicon at room temperature and 0.67 electron volts for germanium at room temperature. Okay, then we have seen that the Fermi level, intrinsic Fermi level, lies in between. Otherwise, in general, any Fermi level lies here. So generally for N type of semiconductors, the Fermi level lies above EFI but below EC, and the Fermi level for P-type materials or extrinsic P-type materials, it lies below EFI, or it goes below EFI but remains above EV. So these two are different cases, these two are not same for two different materials. So it will go up, it will come down, and if we try to calculate to the conduction band, so in conduction band is a representation of free electrons, and valence band generally deals with free holes. The concentration is indicated by N. So there are two basic formula which are related with atomic structure or the energy band diagram, very conceptual, very fundamental formula. They are N is equals to Nc e to the power minus Ec minus Ef upon Kt, or it is same as Ni e to the power Ef minus Efi upon Kt. Similarly, the concentration of hole is Nv e to the power minus Ef minus Ev upon Kt, or Ni e to the power plus only Efi minus Ef upon Kt. So you see how to make use of these two formulas. Both are same. Nc and Nv are the effective density of states in conduction band and valence band. Nc and Nv, and Ec minus Ef for the, if we are making use of intrinsic, for the intrinsic semiconductor, Ef will be replaced by EFI. Ef will be replaced by EFI. So these two formula are mainly utilizable for intrinsic semiconductor, although it is not required, but because for intrinsic semiconductor it is this. For extrinsic, the N goes much if it is N type or if it is P type. In N type, N goes much above Ni, and that becomes approximately as the doping concentration. So P comes much less than Ni, and it goes around Ni square by N, which you have already solved as Nd, so we can keep it here. Similarly in P type, P is going much above than Ni, and it is approximately as the acceptor impurity concentration, and the minority carrier N is much less than Ni, which is approximately as Ni square upon P from the mass action law. So that is how we do it, but it is interesting to see that if we have such a simple relation, then why we go for this? Because the problem statements may be different. If problem statement comes from the band diagram, so these are the relations, or these are the methods for band diagram problem statement. So if the problem statement maintains the band diagram relation, energy band relation, anything is happening with respect to EFI or EC or EV, then we have to utilize these two equations. And once one is known, that is majority carrier, then minority carrier is quickly known as N is calculated, so N into P has to maintain Ni square. So another one can be calculated from this. And this will be utilized when doping phenomena or doping concentration is given in the problem. So okay, so the main thing in the semiconductor theory revolves completely around this, and once the carrier concentrations are known, then we move for the benefits of that. That means we move for total J current density, and before that we define the drift velocity. We drift as the drift velocity for N plus drift velocity for P. We do not bother whether it is N-type material or P-type material. We should always start with the generic form. The drift velocity of both will be in collaboration, or they will contribute to each other. And for drift velocity, an electric field is required, so that is mu Ne, and this is mu Pe. And as per our scope, we'll assume that the electric field is not very high, so that we are not involved in the mobility degradations, and mobilities are always constant for our case. So therefore very simply we can write this, and then later on we can decide which is much more. But effectively, if you see in this, the carrier concentration will not come, so in up to the drift velocity it will not come. But for conductivity, if you see, sigma total will again be, sigma is NQ mu in general, NQ mu N and PQ mu P. Then we can write total current density as drift plus diffusion. Now into drift we can write both the components, that is J drift N plus J drift P, plus in diffusion we can write both the components. So first of all, let me write J drift N as sigma into E, sigma N into E, all due to drift current density due to electrons, plus drift current density due to holes. Now if you see this, this is nothing but this is nothing but this, plus the second term is diffusion, and that is dnq dn by dx minus dpq dp by dx. Minus sign comes for the hole diffusion current density, or because the holes are moving in their decrement area or towards that region where they are decreasing in amount, so therefore there comes the minus sign. So this is the total current density. So in drift, diffusion, as well as in the total current density, we can make use of the carrier concentrations which we have calculated in two methods. So this method or this method depends the type of problem statement. So this is the main part what we have seen, and based on that we'll be using any. A part of that we have seen lots of theoretical concepts, they are important, like we have seen the intrinsic carrier concentration relation. So lots of things are still asked with respect to Ni. Ni square is A naught T to the power 3 e to the power Eg upon kT. So anytime we can calculate this with this is Eg upon kT. So anytime if you keep, it's a big number, and if we increase temperature or if we do anything here, we can calculate the Ni square. The minus sign is absorbed inside. So that also is equally useful. Okay, so here is the problem of gate 2008. Let's say that silicon is doped with boron, that is acceptor impurity concentration of this much. Ni is given. When it was not doped, then the concentration was this, and Kt by Q if required will be this. Compared to undoped silicon, the Fermi level of doped silicon. So compared to undoped silicon, the Fermi level. Okay, so it means it has been asked that the undoped silicon will have Fermi level at EFI, and because we are doping it with the boron, that means acceptor impurity, so finally after that this will become p-type. So for a p-type or doping, acceptor impurity concentration introduces lots of energy levels here, so finally the Fermi level comes down. So Fermi level comes down, and it has been asked that compared to undoped silicon, Fermi level is this, the Fermi level of doped silicon is this. So how much is the difference? So one thing is very sure, that it goes down. So out of these four options which were given to us, it goes down. Either this could be correct, or it goes down, or this could be correct. So out of these two we have to calculate what is the number, how much it goes down. So that we have to calculate. So this is the final Fermi level, EF of the extrinsic. So that means we have to have some relation with EFI and EF. So it is very well known. That is, so because it is becoming a p-type material, so P, which is approximately Na. And one important point to note that we can confirmly write this is to notice that the doping concentration should be at least 2 orders or more than that to the intrinsic carrier concentration. So that is around 10 to the power 10, and doping concentration is too much. So there is no doubt that the final majority carrier, that is whole concentration, will definitely be equal to the impurity concentration. So that is, biformally is Ni e to the power EFI minus EF upon KT. So why we started with this? We had another one also, that is NV e to the power minus EF minus EV by KT. We could have gone for this as well, but because directly there is a requirement of EFI and EF, so it is better to move with this formula. Okay, so this has to be calculated because this is delta EF, the shift. All these four options are given as shift, because we know that absolute value of any energy level cannot be written out there, we cannot mention it, so therefore this has to be identified as Ni e to the power EFI minus EF is delta EF by KT. So this side, or let me write, this is the point which we have to determine. So e to the power delta EF by KT will give us P upon Ni, and P is Na, so it is Na by Ni, and taking ln both the side, delta EF will be KT ln Na by Ni. So if I now write the value, already it has been seen that it goes down, Fermi level goes down. So, but already because delta EF is EFI minus EF, so we are expecting a positive value. So KT is the corresponding thermal energy to the thermal voltage. So the thermal voltage is this much millivolt. So the thermal energy, which is only KT, is the same value but only electron volts. So it is 0.025 electron volts, because this 25 is milli electron volts, so 0.025 into ln. Na is given to us, is doped with this, is ln 4 into 10 to the power 17 upon Ni been given as this 1.5 into 10 to the power 10. So if we calculate this, we get this much electron volts. So we get a value of 0.4274 electron volts. So this is the answer, so not this. Okay, because we have already seen that by this amount it will go down. Okay, so here is the another problem, mainly the theoretical problem. I have just changed the statement of the problem. I am writing that statement in the symbolic form, but I am using the same term or same representation almost in the symbolic form, which have been just been asked in the examination GATE 1987. Being said that two energy levels are there, E1 and E2. E1 is E electron volts above Fermi level, E2 is E electron volts below Fermi level. P1 is the probability of E1 being occupied by an electron, and P2 is the probability of E2 being empty. And it has been asked that which of the four options is correct. A, P1 greater than P2, B, P1 equals to P2, C, P1 less than P2, and D, none of these. Okay, so you see, if I represent the statement in the form of the diagram, then it comes like this. This diagram, if see, it has been said, and because there is nothing mentioned about intrinsic or extrinsic, we can take any example, and just to make it generalized, we can take extrinsic also. So if it is EF, and then this is EC, conduction band edge, valence band edge, then we have understood, we have seen that the Fermi-Dirac function is basically symmetrical about the Fermi level. In extrinsic semiconductor, the Fermi-Dirac function is symmetrical about the new Fermi level, but not the intrinsic Fermi level. So if I now plot the Fermi-Dirac function, then it should go something like this. So at Fermi level, this should pass through a value of 0.5. So it must be something like this. So I have tried my best to make it to maintain it. So now if there is an energy level, let's say at this much distance away, so this is E electron volts above the Fermi level, so this is E1, and so this is under the coat, and E2 is another energy level, E electron volts below EF. So below EF, the same gap below EF somewhere here. So this is E down from Fermi level, and that is indicated as E2. So we know, not being said, the P1 is the probability of E1 being occupied by an electron. So analytically, if we look at this, then this energy state being occupied by an electron, that probability is P, and that probability in this graph is this distance. So this is this probability, this much value, this very small value. And E2, P2 is the probability of E2 being empty. Being empty means occupied by a hole. Means there is no electron in the valence band somewhere E downwards. So EF, the E value downwards goes to E2, and this difference is nothing but 1 minus FFE. So this curve is FFE, which gives the probability of a state being occupied by an electron, and 1 minus of this, and from this distance if we calculate, then we'll be getting the probability of an energy state not being filled by an electron, 1 minus FFE. So this value is the probability that an energy state is empty or is filled by a hole. So both things will be same, all because the Fermi level, the red curve is symmetric. So if we move up or we move down, it symmetrically varies. So at any energy level above, if there is a probability of being filled by an electron, it will be same as the probability of not being filled by an electron at the same energy level downwards. So analytically it says that P1 should be equals to P2. Or if we want to confirm it mathematically, then we have this value as FE1 is equals to 1 minus 1 plus e to the power, I'm just writing the formula for Fermi-Dirac function. So this is E minus EF, so it is E1 minus EF by KT. And this we have already seen, if E is sufficient enough, still even if it is not given, we know that for all practical interest, E is generally a high number. So E1 minus EF is this only, that has been given as E. So I can replace that E, and E is definitely much higher than KT. So if E is much higher than KT, then e to the power, any significant power is definitely greater than 1. So this approximately it overtakes on 1, and then therefore it comes as e to the power minus E by KT. Okay, and similarly if I try to solve E2, but being said that being empty means not being filled by an electron. So what we have to calculate is this. So this was P1 and this is P2. So this is 1 minus 1 upon 1 plus e to the power E2 minus EF. E2 minus EF will give me minus EF minus E2 by KT. Now you see in this case, this is EF minus E2 is nothing but E. Now again, by the same token, if we see that E is much larger, but in spite of solving everything here, we can take 1 minus of this, so that becomes 1 plus e to the power minus E by KT, and this goes here, 1 minus 1 cancels 1, it becomes by KT. Okay, now we can compare 1 plus this. So this is a very small number, because e to the power anything which is minus significant, and this is a significant number, because we know for all practical purposes, all feasible purposes, the E is definitely much greater than KT, because KT is very small, very poor number, 0.026 electron volt. So we know that e to the power minus a big number is definitely approximately 0. So that approximately gives us 1 plus 0 remains 1 only, so it is e to the power minus E by KT. So you see P1 is this, P2 is this, so therefore it confirms P1 is equals to P2, which again confirms mathematically that it is this. But we should understand and we should identify from a general nature that for any intrinsic or extrinsic semiconductor, the Fermi level always remains symmetrical about the final Fermi level. For intrinsic, the final Fermi level is the original intrinsic Fermi level, but in the extrinsic, either the Fermi level, the Fermi Dirac function shifts up or it shifts down, but always it remains symmetrical about the Fermi level. Okay, so this is the next one. At any temperature T, the band gap of intrinsic germanium is this, although it doesn't suit to the value at room temperature, so this must be some very low temperature or absolute zero, but whatever it is, we'll not argue with this. Whatever band gap is given to us, will not argue with that value, with the memorable value to us. So we'll take it as it is. The intrinsic carrier concentration of germanium is this, and it has been asked that to generate electron hole pair, which one of the wavelength ranges is most suitable. Means out of these four options, which wavelength will correspond to a breakage of a covalent bond and it will generate one electron hole pair. The required data, possibly required data, Planck constant is this, velocity of light is this, electronic charge is this. Okay, so you see, again the question is finding its fundamental on to this. So if one electron hole pair has to generate, then at least a transition must happen from valence band to conduction band, because we know that a covalent bond breakage is equivalent to this transition. So one covalent bond breakage is equals to the transition. So both are the same thing, but this is from the understanding of atomic diagram, atomic structure diagram. This is from the energy band diagram. So if we see, we require this, and whenever any incident light or any wavelength falls on the material, it absorbs, the material absorbs h c by lambda, where c by lambda is nu, so most of the time we call it h nu as well. So let me write it like this, h nu, or we call it nu is the frequency, c by lambda, c is the velocity of light. So this energy should be at least greater than band gap, so that when material absorbs this energy, then a transition occurs. So it should be at least greater than the difference between EC and EV, so it should be greater than or equal to this. So the equal value will correspond to the minimum, the maximum wavelength here. So this is the minimum energy and this will be the maximum wavelength. So now if I solve from here, this hc by lambda c should be equals to Eg, or hc is a well-known value of around 1.24. Otherwise we can anytime multiply h into c, and if we do so, we will be getting a value of this range. So 1.24, then lambda c is 1.24 by Eg, and it is 1.24 by Eg. The band gap is given as 1.42. Okay, so this much micron directly. Okay, so but please don't bear with me, you go and identify, because for that sake only, because I remember so just to save time, just to only elaborate the concept, I am just directly writing it. Otherwise one need to multiply these two things and you will get that this is the value, and this gives me hc is equals to 0.874 micron approximately. So if this is the wavelength, then that should be the maximum wavelength, because anything greater than that will lower the energy, because this comes in denominator. So anything greater than that will lower the energy, so the transition will not happen. So hc max should be this, or otherwise it should be less than or equals to that. So therefore the only option here is option A with this. So the another problem is a silicon sample with unit cross-sectional area is in thermal equilibrium. Temperature is given, other constants are given if it is required, and especially the electron mobility is given, as the sample is n-type because the donor impurity concentration has been given. The magnitude of E is for electric field. The magnitude of electric field at x is equals to 0.5. So somewhere here, what will be the electric field, that we have to know, we have to calculate, and I have not given any options because it is not required here. We will calculate the absolute value without having any idea of this options. Similarly, the magnitude of the J drift, that means the drift current density at x is equals to 0, means here we have to calculate the drift current density. Okay, so this is generally based on the concepts of understanding how an electric field is distributed within a semiconductor. So please remember, whenever the electric field is sustained or maintained if there is a static charge concentration. The main concept is the electric field in a region is sustained, that means maintained at a constant value if the charge concentration is uniform and maintained. So if the charge concentration is uniform and maintained, then the electric field in that region is also maintained. It doesn't vary. And whenever there is a change in charge concentration, either sudden change or gradual change, then we can expect the electric field to be changed also. So within a metal, we have already discussed in the theoretical part in previous lectures that within a metal, because there are lots of carriers to respond to the electric field, so electric field is no more sustained within the volume of the metal, because as soon as we apply an electric field, lots of carriers are there, lots of free electrons already are there to respond to it. So it is not possible to for electric field to remain maintained within that, because it vanishes, because everything is for that cause there is a result. Okay, but for any insulator there is definitely a perfect electric field, and that always remains constant within an insulator, because within insulator there is no free carrier, there is no charge distribution within any type of charge carrier, so or any type of charge. So if within an insulator or within the volume of an insulator, the electric field remains constant, sustained at some value, depends on the terminal ends of the insulator conditions. In semiconductor, there is a diplomatic scenario. If it is given that there is thermal equilibrium, this is the main part of this question. If thermal equilibrium is given, that means a uniform carrier concentration is maintained everywhere. So it means that a uniform carrier concentration is maintained everywhere. So if carrier concentration is uniform and maintained, therefore the charge concentration is also uniform and maintained, and if there is no variation in the charge, then as just we elaborated that then the electric field has to be constant. So that means the electric field will remain constant throughout. So it is like a capacitor plate, two plates, and within there is a dielectric or insulator. If we apply a potential difference, then within the gap of that capacitor the electric field remains fixed, because within an insulator there is no charge carrier or there is no charge concentration. So even if there is no charge concentration, then also electric field remains sustained or maintained at a constant value. Or if there is a charge concentration but it is throughout uniform and maintained, then also the electric field remains constant at some particular value. So that's what is happening here. So simply in case 1, the electric field magnitude will be the potential difference between the distance. So the potential difference is 1 volt from here to here. So this is plus, this is minus as per the polarity. So it is potential difference divided by the distance across which this potential is maintained. So that is 1 micron. So it is 1 volts from upon 1 micron. So maybe if the We'll check out in the answer. So possibly in the answer the all the values were given in volts per centimeter. So if values are in volts per centimeter, we can write it 1 volt upon 10 to the power minus 3. This is 10 to the power minus 6 meters, or we can write it 10 to the power minus 3 centimeters. So if it goes up, it becomes 10 to the power 3 volts. Then this is 1 kilovolts per centimeter, because 10 to the power 3 goes there, and then it becomes 1 kilovolts per centimeter. Okay, so this is the answer. So out of the 4 options, we'll be looking at this answer. And second, the magnitude of the J drift. Now we know it's very easy, J drift, and here it will be all because of the electrons only, because in the N type where there is donor impurity concentration, that is also very good. Then we can expect all the majority carriers of electrons of heavy concentration, and the holes will be negligible in front of that, at least 7 or 8 orders less than this, at least. So therefore we cannot, it is insignificant to consider the holes. So therefore the J drift is dominantly all due to the electrons, even if we always start with this, but we know that this amount is almost negligible, so it is approximately same as sigma n into E. E is the electric field magnitude, sigma n is the conductivity contributed by the free electron. So that is sigma n is nq mu n E. Okay, so for that, n is the concentration, and we know when we have doped it with the donor impurity concentration of this, then final electron concentration also becomes approximately this. So this is 10 to the power 16 per centimeter cube. Q is 1.6 into 10 to the power minus 19 coulomb. Mu n is given 1350 centimeter square per volt second, and electric field is what we have just calculated is this. So because within everywhere it is this, and we are supposed to calculate it at x is equals to 0, means 0 we can take limit at just 0 plus just after that. So within 0 to 1 micron there is throughout constant electric field of this value what we have just calculated in previous section. So this is 10 to the power 3 volts per centimeter. So with that we get an answer of mho per centimeter. Obviously the final unit should be this. Separately we have written all the units, and it comes as okay, one small mistake here. 10 to the power minus 6 meters is not 10 to the power minus 3, it is 10 to the power minus 4 centimeter, because it is not millimeters or this, so it should be 10 to the power minus 4. Okay, so please mind it, this is a small correction, numerical mistake, calculation mistake. So if it goes up, it becomes 10 kilovolts, so I need to correct it 10 to the power 4 volts per centimeter. So if I keep this, the answer comes as 2.16 into 10 to the power 4 ampere per centimeter. Okay, because this is J, not the conductivity, ampere per centimeter is square in fact. Okay, so the next problem is ln of rho I, where rho I is intrinsic resistivity of silicon, is plotted against the function of, as a function of 1 by T. So 1 by T, where T is the temperature, absolute temperature. So the ln of resistivity is as a function of 1 by T, and it has been found that the plot is almost linear. So this is almost linear. and the slope of the line can be used to estimate. So if we somehow note the slope, then it should be somehow related, or it should be giving any of these four ideas. Either it is giving the band gap energy of silicon Eg, or it is giving the total mu n plus mu p mobilities of electron and hole, the inverse of summation of electron and hole mobility, or it is giving the intrinsic carrier concentration. So out of these four options, which one is most appropriate or which one is correct? So okay, so for that to know, we will have to evaluate that how ln rho I is a function of temperature, in what sense. And you see here, because there is ln, so we should expect some exponential thing or exponential relation somewhere. Okay, if we start with the y value is ln rho I, and this I am calling as x value, this I am calling as y value. So I have to get a relation between y and x. Then we will see dy by dx. So we will find the slope is dy by dx. Okay. Okay then. So ln rho I is, I take rho I is 1 upon the conductivity, because we don't have any relation directly with resistivity. We know everything about intrinsic conductivity. So it is minus ln sigma I, or it is minus ln. Sigma I is nq mu, but in intrinsic the electron concentration is also Ni, hole is also Ni, so this is Niq mu n plus Niq mu p. So this Ni is for hole concentration, this is for electron concentration, and if I take this thing common, Q Ni, so Niq is common, then mu n plus mu p. Now we don't see temperature anywhere, so from here we should not expect anything. Now this is almost a constant, so we can only expand the Ni term. So this is minus ln. I can take this one as a constant outside, so it is q mu n plus mu p. Okay, then it remains minus ln Ni. Now this whole thing acts as a constant, but still I can keep it minus ln q mu n plus mu p minus ln Ni, the intrinsic carrier concentration, is some constant, or under root of some constant is also constant, into t to the power 3 by 2 into e to the power minus band gap upon 2kt. Okay, so then if I take ln a naught separately, so this gives me minus ln q mu n plus mu p minus ln a naught dash. Then second term, so these three are products. I am expanding ln into these three terms separately. Minus ln into this will give me 3 by 2 will come out, so this will become minus 3 by 2 ln t. And then for the third one, because it is already exponential, so the whole power comes down. Minus minus becomes plus, so it is plus Eg by 2kt. Now you see, interestingly, in this whole term is a constant. Okay. Now there is temperature at two places, here and here. Now if you see the temperature here, if we try to plot against this, then as temperature increases, the value should get down. So as temperature increases in this direction, temperature increases, so the value should get down. Okay, it is getting down. And here also, if temperature increases, the value gets down. But you see, ln t is already a small value, we are varying it to a smaller value, and ln of any value is much smaller, because a ln function or log function compresses the value. So this is almost negligible. Also because we had to see 1 by t, that directly comes here. So we are plotting ln with respect to, not respect to ln, we are plotting ln with respect to 1 by t. So it is ln with respect to ln. So that we are not interested in, or we can argue that this is negligible also. So approximately this is a constant. Approximately this is a constant like C plus Eg by 2kT. So if it is C plus Eg by 2kT, what we expect that y is equals to 1 by t I have given as x. So 1 by t here is x. So y is equals to C plus mx, where m is the slope. So y is equals to C plus Eg by 2k into x, where x is nothing but 1 by t. So this approximately gives a straight line. Why approximately? Because we are neglecting this thing. So it is being told that it is almost linear. It is not strictly linear. That already in the problem it has been taken care of by saying almost. So this is almost a straight line equation like this, and the slope is this. So this is the slope. So slope here gives us the idea of Eg by 2k. So now we know that k is Boltzmann constant. So if we multiply the slope by 2 into k, then we must be getting Eg, because we know the value of Boltzmann constant. So Eg will be evaluated out of that. Eg is the band gap energy of the silicon. So option number A is correct. So from this plot, this approximately linear line, and this should not be this, this should not be this should be somewhere here, so that the cut is a negative value as from this constant, but we are not really bothered about that. We just want to see the nature as an approximately linear line. The next problem is very simple. It says a silicon bar is doped with a donor, Nd is the symbol for donor impurity, means with some pentavalent like phosphorus or arsenic. Doped with this by 2.25 into 10 to the power 15 atoms per centimeter cube. Okay, Ni is given at room temperature. Assume complete ionization, the equilibrium concentration of electrons and holes. There are 4 options, but we don't require it. We'll just calculate the absolute values. Assume complete ionization. So complete ionization in itself is again verifying that each one atom of donor impurity, will definitely donate 1 electron, 1 free electron. So these many will donate this many. So earlier when it was intrinsic, let us see the development again, although it is very simple. So in intrinsic, N was equals to Ni. N is equals to Ni, and that is 1.5 into 10 to the power 10 per centimeter cube. P is also Ni, means the holes and electron concentrations are both same, and they are very poor numbers. So don't get confused by these numbers. They are very bad numbers in front of the total potential of silicon. So then what do? We add with Nd 2.25 into 10 to the power 15 electrons per centimeter cube. Why electrons? Because with complete ionization, each one atom donates 1 electron. So these many electrons are added. So this thing goes in addition with this number of electron. So this plus this, because 10 to the power 15 is too much. 10 to the power 10 is nothing in front of that. So this plus this becomes this only, 10 to the power 15. So the final concentration, let's say N0, goes greater than Ni. So therefore it becomes N0 is approximately Nd. Nd plus Ni, but it is approximately Nd. So that is the same, 2.25. So let me call it, we have to calculate N0 and P0, means electron and hole concentrations in the final one, in the extrinsic semiconductor. That is 2.25 into 10 to the power 15 per centimeter cube. So N0 is definitely okay. And with P0, what happens? P0 comes down so that it has to maintain the mass action law, or P naught into N naught must maintain Ni square at the same temperature, because temperature is not varying. So therefore if N naught goes high, P naught has to come down, so that to maintain this relation. So therefore P naught will be Ni square by N naught, and this is approximately Ni square by Nd, because N naught is same as Nd, and therefore this is approximately Ni square is the square of this 1.5 into 10 to the power 10 is square upon Nd is this 2.25 into 10 to the power 15 per centimeter cube. And if you calculate this data, 1.5 square is simply this, so this thing will get cancelled with this, and this square will give you 10 to the power 20 divided by 10 to the power 15, so it will be 1 into 10 to the power 5 per centimeter cube. So finally the whole concentration, which is the minority carrier concentration, is this, the majority carrier concentration is this. Okay, so these two are the final values, this and this, and we can find this in the options. Okay, so another theoretical simple problem. It says a p-type silicon sample is uniformly illuminated with light, okay, which generates excess carriers. The recombination rate means as soon as we remove off the light, then the excess carriers or the additional carriers which have been generated, because in absence of light there were the carrier concentration all due to the thermal equilibrium. Now once we focused on light, or when we eliminated it with light, then there will be extra covalent bond breakage, and due to that the excess carriers will be there, both electron and hole. Okay, then the recombination rate is of those excess carriers, that is proportional to minority carrier mobility, minority carrier recombination lifetime, majority carrier concentration, excess minority carrier concentration. Okay, so we know that this is when the recombination rate and generation rate we talk about, and in this type of scenario, a uniform illumination or illumination at some corner or this special region, special corner of a semiconductor, we know that these are the cases of thermal non-equilibrium momentarily. So therefore if we know that we can only proceed with the continuity equation. So if we remember, the continuity equation says that we can write the electron or hole concentration rate, or the change in rate of change of carrier concentration, like let's say I write del N by del T. So this is generation rate minus recombination rate. I wrote N0 minus N0 upon tau n. So if I'm writing this equation for the electrons, then it is this plus 1 by Q into delta, means the space derivation or spatial derivation of the total current density. It involves drift as well as diffusion, both the components. So this, I'm not expanding this because this is the term of interest. So we know, because as soon as we remove off the light, the recombination, this rate dominates over this. So we should not forget that this whole thing is the recombination rate, UN, and UN recombination rate is directly proportional to N0 minus N0. And N0 minus N0, N0 is once we start observation of the diffusion or the recombination process. N0 is after a long time the excess values will come down to their settled or steady state value. That value is N0. So this is this, and we had seen the profile that with respect to time, if we see at this moment when we start counting, this is the concentration and this is the excess at t is equals to 0, that only we call, and we know that profile goes like this. So after a sufficient time they go. So this is the steady state concentration, which should have been in the absence of any elimination or any additional thermal energy. So this should have been the case, but all because we had up to this there was elimination, and we removed all the illumination. So suddenly after that diffusion process will significantly take place, and this difference, the rate of recombination will be in proportion to this difference, and this difference is the N0 minus N0, which is called the excess carrier concentration. So definitely the recombination rate depends on this. Means if it would have started from here, then it would have gone something much more rapidly. So if we place a slope here, here it comes as this, here it comes as this. So the slopes will be different. That means the rate of recombination will be different if this value is high enough. So therefore, out of these four, the recombination rate is directly proportional to the excess carrier concentration. Now minority, because I argued that this development of uniform illumination happens like this. So let's say this is a p-type material. So there are lots of holes, like p, they are of the order of 10 to the power 15, and n, they are of the order of 10 to the power 5, let's say. And all due to that, and all due to the illumination, there happens excess carrier generation because of illumination, because of the additional energy. So some additional covalent bond will break, and due to that some delta P amount, which is approximately 10 to the power 8 will happen, let's say. And similarly the same amount of holes and electrons will generate due to any additional amount of energy or covalent bond breakage. So this will also delta and will also be around 10 to the power 8. Now this 10 to the power 8 or this number is nothing in front of this, so it will still remain at this, so we can forget about this phenomena. So any excess carrier above the steady state or equilibrium value proves to be negligible for majority carriers. So there is no consideration of this excess carrier for majority, all because the excess carriers for majority are negligible in front of the already existing majority carrier concentration. But for this minority carrier concentration, already existing minority carriers were very small in numbers. So anything in excess of that will be significant enough. So it will be much more interesting, much more significant to observe the minority carrier concentration. So I've discussed this earlier in the lecture that the diffusion process through which the recombination happens is much more significant for the minority carriers. So this confirms this, and we have already seen that it is directly, this is the recombination rate, which is in proportional to that, which is the excess minority carrier concentration. So this is a theoretical example which proves our argument in a thermal non-equilibrium case. Okay, so the next one is also very simple. It says that a silicon sample is uniformly doped. I have not written the complete statement, but it says the silicon sample is uniformly doped with the donor impurities of this. So if it is doped with donor impurities, so this must be the final electron concentration, because this seems to be pretty high. And assuming complete ionization, which we by default assume, even if it is not given, we assume that each one atom, impurity atom, donates or accepts one electron. So if it is donor impurity, it definitely donates one electron. So if one atom donates one electron, these many atoms will donate these many electrons. Find the resistivity in this. Okay, this is very simple. We know that resistivity is nothing but conductivity. So once we calculate conductivity, we can calculate, or from a starting itself we can write this is 1 upon this, and the complete conductivity is n q mu n plus p q mu p. We should always start the total conductivity with this combined formula, then we'll decide which to be considered and which could be neglected. So here, as we have seen that it is doped with the donor impurity, so N becomes final electron concentration is Nd, that is 10 to the power 16, and therefore P, which will be given by the mass action law, Ni square by Nd. And even if Ni is not given to us, we know that because N is a better number, this is very poor number. So the consideration of this is not required. This is, I'm saying this is not significant here. So this approximately only remains as 1 upon n q mu n, n is nd, nd q mu n only. So even if the Ni was given, although Ni is not given, just to emphasize with our concept that it is not required to calculate it, otherwise Ni would have been given. So nd q mu n is 1 upon nd, nd is 10 to the power 16, q is 1.6 into 10 to the power minus 15, mu n only is required, this is 1200. So everything in centimeter units everywhere, so I must expect resistivity in ohm centimeter. So this gives me 0.521 ohm centimeter. This we can calculate and confirm this. That is the. So in the next problem, an n-type sample is uniformly eliminated, and if it is done so, then 10 to the power 20 electrons and hole pair per centimeter cube per second are generated. So this is the rate of generation of excess carriers, or the over the intrinsic or the prior concentration. If minority carrier lifetime is 1 microsecond, then if in the steady state the whole concentration is this, then find the x. That means ultimately we have to determine the whole concentration. Whole in the n-type sample acts as a minority carrier, so that is okay. We only expect the significant improvement in minority carrier concentration. So what has happened is like this, that there are two instances that up to this time t1 and this time t2. So earlier the whole concentration was maintained at n1, the whole is pn1 at concentration pn1, and there is no elimination. And after that we give the elimination. So at time t1 we start eliminating it uniformly. So as soon as we do so, the carrier concentration, and we are only focusing on to the minority, but same thing happens with majority. But because in majority the excess amount is negligible in front of previous amount, so we are not considering it. So the minority Pn, the holes concentration in n-type material, that means minority carriers, it was at level at Pn1. Then as soon as elimination goes, then it increases, and maybe it should be like this. So at some time t2 it approximately comes to the newer value. So in this phase, this is called the thermal non-equilibrium. This phase, which is the transient phase, suddenly what will happen, the generation rate will exceed the recombination for holes. If we are writing, so the generation rate will exceed the recombination rate. Before that, because everything was kept without any elimination, so this was thermal equilibrium case, and generation rate was same as recombination rate. Then suddenly we started eliminating it, then suddenly the generation rate will boost up, it will try to settle at a newer value. So the time up to which it has not settled yet, T2 minus T1, so this time phase will be a transient phase, thermal non-equilibrium phase, when generation rate is greater than recombination rate. So therefore it will take up the final concentration, and suppose that newer value Pn1, this goes to Pn2. Definitely Pn2 is much greater than Pn1, because that is maintained, elimination is maintained. And then again things are coming into the thermal equilibrium, so again generation rate will be same as the recombination rate. And once this happens again here, then we can see that this is the excess amount. But this excess amount is not diffusing totally, it is not, because we have not removed of this. As per the problem statement understanding, we are not removing so the there is a new settlement at some newer value. So therefore there's excess amount, if we see, which is not getting recombined totally, so they are not being washed away, they are not being removed away, so they are maintained. So we know that recombination rate is same as generation rate after T2, once the steady state is achieved. So in the steady state, so thermal equilibrium means the steady state is achieved. But from T1 to T2 there was a transient state. After T2, because everything has been finalized, the excess amount has been obtained, so that is called a steady state. So in a steady state this is again maintained, and this is same as Pn2 minus Pn1 upon the carrier lifetime, and we are considering holes as a minority carrier in n-type, so it is this. But what we can see, definitely Pn2 goes much above Pn1, so that's a new value. We can forget about Pn1, we can absolutely measure Pn2, so therefore it is negligible, and it is approximately Pn2 by tau p, and we have to calculate this newer value only. The whole concentration we have to calculate finally in the new state, in the new steady state. This was earlier steady state, now it is a new steady state. Okay, so therefore Pn2 is approximately equals to tau p into generation rate. So tau p is given, carrier lifetime is 1 microsecond, that means 10 to the power minus 6 seconds into Gp. Gp is the generation rate, this much, 10 to the power 20. Electron and holes as well, but we are considering holes per centimeter cube per second. Second will get cancelled. So these many holes per centimeter cube. So this is 10 to the power 14 holes per centimeter cube. So this is the new value, 10 to the power 14, and we are asked for x. So 10 to the power 14 means x is 14 here, because x has been demanded here in the problem. Okay, the next one, the resistivity of an n-type silicon is given, the electron mobility is given, find the donor impurity concentration. That means into intrinsic we must have doped some donor impurity, so that final semiconductor becomes n-type. Once it becomes n-types and it is being measured, the conductivity or the resistivity actually comes as this. So we know that the resistivity is 1 by conductivity, and this is 1 upon again nq mu n plus pq mu p. But we know that for n-type the n is greater than p, and the n is approximately nd. So therefore we can neglect this, because p is much smaller than n. So if we neglect this, this becomes 1 upon nd q into mu n, and therefore we have to calculate nd. So nd is basically 1 upon approximately q mu n. That gives me, resistivity has been given 0.5. Just check whether everything is in centimeter or not. Q is 1.6 into 10 to the power minus 19 into mu n is 1250. So if we keep this value, we are expecting some value in the centimeter per centimeter cube. So that comes as 10 to the power 16 per centimeter cube. So this is the answer. Okay, in this problem, silicon sample A, there is some sample, is doped with boron. So if it is doped with boron, that means it becomes a p-type. The majority carriers are holes, 10 to the power, and the impurity concentration is 10 to the power 18 per centimeter cube. Another sample B is doped with phosphorus, that means it becomes n-type, and the impurity concentration is again 10 to the power 18 per centimeter cube. It is given that electron to hole mobility ratio is 3. Then the ratio of conductivities of sample A to B is, that means We are supposed to calculate the ratio of conductivity A to B, conductivity of sample A to conductivity of sample B. Now the sample A finally becomes, because we are doping it with this, so this is nothing but Na, means acceptor impurity, so finally it becomes P type. This is nothing but donor impurity, because phosphorus and arsenic are donor impurities, so finally it becomes N type. So this is same as P upon sigma N. Sigma P is PQ mu P upon this is NQ mu N. And we know that in extrinsic P-type semiconductor, the majority carrier holes has the same concentration as the acceptor doping concentration, 10 to the power 18. So P is 10 to the power 80. Q and Q are cancelled into mu P by mu N upon N. Also we can write N is ND, which is 10 to the power 18 again, into mu P by mu N. Mu P by mu N is 1 by 3. Okay, so this thing gets cancelled and it is 1 by 3. So it is the answer. So the ratio of conductivity will be this. So in the next problem, a heavily doped N-type semiconductor is given, and into that holes to electron mobility ratio is 0.4. The doping concentration is this, and it is very clear because it is N-type, so this is definitely ND, the donor impurity concentration. Intrinsic concentration is also given, and the ratio of conductance of the N-type semiconductor, conductance of N-type semiconductor to the intrinsic semiconductor. So we have to write the conductance of N-type semiconductor to the intrinsic. Now we know the resistance is 1 by G, or G is 1 by R. So that means we have to find this. We have to start from here, and it is 1 by Rn upon 1 by Ri. The total resistance of N-type upon the total resistance of intrinsic, and this if I write Rin upon Rn type. So resistance is nothing but resistivity L by A, some dimensions of intrinsic, upon resistivity of the N-type, finally extrinsic semiconductor, into the same dimensions because of the same material of the same piece. So this thing gets cancelled. So rho in upon rho n. Rho in is 1 upon conductivity of intrinsic. Resistivity of N-type is 1 upon the conductivity of N-type. So this was pretty obvious from here itself, but if one is not identifying that how to start with conductance, because it is not conductivity here, then we can proceed like this. But very starting itself, we know that conductance is directly proportional to conductivity, because the dimensions will get cancelled for the same material or same piece. Okay, so therefore it is sigma n upon sigma n. Sigma n is nq mu n plus pq mu p, but pq mu p is definitely very, very small because it is heavily doped N-type. There is no question of minority contribution into the conductivity. So this remains this upon intrinsic is niq mu n plus niq mu p, because in intrinsic electron and hole concentration, this is hole concentration is same as Ni, electron concentration is same as Ni. So therefore, now N is nothing but the doping concentration Nd, and please mind it that here the values are given not per centimeter cube but per meter cube. But it is okay because both values are per meter cube, so the ratio will be unaffected. Okay, so it is Q will get cancelled, so it is Nd mu n upon Ni could be taken common, mu n plus mu p. Now because we know mu p by mu n, so we can divide it by mu n, numerator and denominator. So mu n upon mu n is 1, Ni 1 plus this. So Nd is given. This is the doping concentration, 4.2 into 10 to the power 8 upon Ni is this 1.5 into 10 to the power 4 into 1 plus mu p by mu n is given as 0.4. So this thing comes as 20,000. So this is one of the options given to us. I have not given the options, but this we can absolutely determine as an answer. So as is expected that the conductance of the extrinsic should rise much because the conductivity rises. So this is nothing but conductivity, this is nothing but conductivity. So because we are moving from intrinsic to extrinsic just to make benefit of higher conductivity or higher conductance. So this much improvement we are getting at the final conductance. So this is the improvement of final conductivity. So the next problem here is that a silicon sample is doped with 10 to the power 16 phosphorus atoms. Okay, but it is also doped with 2 into 10 to the power 16 boron atoms per centimeter cube. And it is being told that if all the dopants are fully ionized, all the impurity atoms are fully ionized, then the material will become N-type with this, P-type with final majority concentration is this, P-type with final majority concentration is this, and N-type. So out of these 4 options, which one is correct? So you see, even if this is not given, if all the dopants are fully ionized, we know that we will assume this case. Otherwise the percentage ionization will be given to us. So all the 10 to the power 6 phosphorus atoms, they provide all 10 to the power 16 electrons. Similarly, all boron atoms will provide all one hole each. So these many number of holes. But here it is the composite doping case where this amount is Nd, this amount is Na, and if we closely look at this, Na and Nd are comparable here. Although still Na is doubled of Nd, but there is not the difference of any order. So we know that if the order is at least greater than 1, means 10 to the power 1 order difference is there, then at least we can consider Na is greater than Nd or Nd is greater than Na. But here the order remains same, only it is the twice of this. So here we will have to take extreme care of this case, and we cannot finalize, though it looks that all because boron atoms are more, so Na is greater than Nd, so definitely it tends to become a p-type material. So therefore we are tempted to, there is a hint to find from the exact formula Na minus Nd by 2, this we have seen in the lectures, plus root. Okay, and why we have chosen P? All because there is a hint that Na is greater than Nd. If Nd would be greater than Na, we would have gone for N is equals to Nd minus Na by 2 and like that. Okay, and in this, although Ni is not given to us, but with some very basic knowledge, we know that this doping concentration is quite high or moderate or high doping concentration. So definitely it is far greater than Ni. So there is no question of considering Ni, because whatever happens with Na and Nd, the order definitely will come into the 10 to the power 16. So even if it is not known, we can very easily guess that this would be negligible in front of this. So this is we can solve this also. 2 into 10 to the power 16 minus 10 to the power 16 means 2 minus 1 is 1, plus the same thing 2 into 10 to the power 16 minus 10 to the power 16 upon 2 square under root. So therefore here it is 10 to the power 16 by 2. Here also it is 10 to the power 16 by 2 square. So after under root this becomes, so this is 10 to the power 16 by 2. Oh, I'm sorry, 10 to the power 16 per centimeter cube. So this is the answer. So finally this is the concentration of holes, and as we expect, all because Na is greater than Nd, so this leads us to the p-type material, and therefore we started with majority concentration and we founded this. Once it is founded by founded this manner, then we can definitely go for N is equals to Ni square upon P from the uh, mass action law. And please mind it, here P is not equals to Na. So here P is not equals to Na, because this is the approximation only. Whenever in the composite doping the other polarity, other type of carrier is also very high, then we cannot directly come to P is equals to Na. Okay, so this is the case. So P here is this, where Na was 2 into this. Okay, so in this Ni square is not known to us upon P, but if it would be given to us, upon P would be 10 to the power 16, and we would have obtained something here. Okay, but that is not been asked. So Ni we know by our prior knowledge, but will not be using here. So it is it gives some sense that okay, I'll little bit extend, although we have found it 10 to the power 16 with P type, so that goes here for option B. Okay, but some extension to this problem, to the explanation that what happens with the minority carrier, with the N. So it looks like N should be this and P should be this. So this has been proved wrong here. Here P is not this, it becomes half of this. So what about N? This is definitely wrong, because N comes here, if we go with our prior knowledge, Ni is 10 of the order of 10 to the power 10. 1.5 into 10 to the power 10. I am just making it 10 to the power 10. So its square will be 10 to the power 20. So this will be approximately 10 to the power 4. Interesting. You see here, this is the concentration of final electrons. We were expecting it to be 10 to the power 16, but this happens. So what is this scenario? Means as soon as we combine these two, so they are over this, means it is like this, N which is equals to Ni was, I'm writing this story here, what has happened here. Earlier in the intrinsic case, what was the story? N was equals to Ni, that was 10 to the power 10, P was equals to Ni, that was 10 to the power 10, and N into P was Ni square, so that is equally valid. Then over to that we added further these many number of electrons, so Nd which was 10 to the power 16, and then we added Na 2 into 10 to the power 16, and then what will happen? We for the time being we can forget about this amount, because this is very small amount. So almost all of these electrons will quickly find the lots of holes available. See, if this would not be there, this was not there, then all these electrons would have found this many holes. So therefore some small number will be reduced from here and they would have gone here. But all because all the electrons are finding holes here, and holes are finding lots of electrons to get recombined. So all due to the recombination, 10 to the power 16 electron will recombine with 10 to the power 16 holes. So half of the holes are gone. So what remains is 10 to the power 16 holes and nothing out of it. In fact, still lots of holes are available to recombine further electrons. So this also gets, so this has completely gone, and therefore this also reduces, because still the holes are too much to recombine with lots of holes. So it goes to 10 to the power 4 as we have expected. So this is a rough story of this whole picture. Although it is not a practical, not a desirable case to have this kind of composite doping, because it leads us to very confusing case, but this happens most of the time in the integrated circuit fabrication, that we do not have a neat situation all the time, that it's pure intrinsic thing and we are doping something extrinsic into it or some impurity into it. There may be a scenario that already an N-type region is established. Onto that we have to locally develop a P-type region. So onto top of that we have to have a acceptor impurity concentration of more than the bulk or base P-type N-type region. So in that scenario this is a practical or relevant data. Otherwise, if we are going to start with finally a P-type or N-type from the intrinsic silicon, we are never going to have this case as a practical one. Again, a problem of same style, an easy problem. It says a silicon sample, intrinsic silicon sample of this intrinsic carrier concentration. It is doped with both donor impurity concentration and acceptor impurity concentration. And just by looking at it, we can easily appreciate that the acceptor impurity concentration is definitely far greater than this. The approximate number of electrons per centimeter cube finally. So as we are observing, Na is greater than Nd. Why? Because we know that even if it is more than one order, then we can consider this case. But here it is there is a difference of 3 orders of 10. So definitely there is no doubt that Na is greater than Nd. So finally it becomes a p-type material with majority carriers as holes. So P here will be approximately Na. So here there is no need to go for a detailed formula like Na minus Nd by 2, because Nd would be nothing in front of Na. And then if we have to calculate the minority carrier N, so from N into P is equals to Ni square, we can write N is equals to Ni square by P exactly, or approximately Ni square by, because P is approximately Na, and this value would be Ni is this 1.5 into 10 to the power 10 square upon Na. Na is this. Okay, so if we try to calculate it, it comes around, you see, this is a value 220.25 into 10 to the power 20 upon 10 to the power 18. So it is, okay, 225 into 10 to the power 2 per centimeter cube, or 225 electrons per centimeter cube. So this is the answer. Okay, so this one is the interesting one. Which one of the following represents the energy band diagram for the biased n-type semiconductor shown? So the n-type semiconductor has been biased like this. So this comes as the positive terminal of this. Here it is the negative as per the sign convention. So for this piece of n-type semiconductor, if below this we show the energy band diagram, then which one of the 4 possible cases will be correct? Now if we see very clearly, we need to understand 2 important things here. We have already discussed one important point is energy band diagram represents the increasing order of energy for electrons. Okay, so if it is n time, it is full of electrons. So therefore this side, if you see, one more thing is this, that if we have seen in a previous problem, that if this type of battery is applied and if the potential is dropping from here to here, then that means there is an electric field within this in this direction. Okay, and it would be almost sustained if the concentration of the impurity concentration or the electron concentration everywhere is uniform. So if the carrier concentration or charge concentration is uniform, then electric field would be sustained. So this side of the region will be having the positive polarity, this side, and this is not the abrupt change, there will be a linear change. So linearly the potential is rising like this. So for this corner of the n-type semiconductor, or for the electrons, because it is full of electrons, so everywhere there are electrons, free electrons, lots of free electrons. So this side of the corner, the electrons will find a favorable scenario, they will find the positive potential. As soon as they find a positive potential, they will try to lower their energy, or their energy would be lowered, because that is the favorable condition for a negative charge, electrons, to get the positive potential. So the energy would be reduced, and if we want to further agitate, further make them cry, then we'll have to give a negative polarity to the negatively charged particle, that is electron. And so therefore if we give the negative polarity to this side of electrons, then the energy will boost up. So it is like this side of the electrons will have higher energy and this side of the electrons will have lower energy, and this will change linearly because this potential is not changing abruptly. I'm just showing for the simple case, it is going linearly. So therefore it is very clear, energy band diagram, even if the Fermi level is not given to us, we know that the electron's energy is given by the any energy band or any energy level. So it must be like in the fourth option. So it is like and here please mind the point that I am not only showing the free electrons, I may also show the bounded electrons. But if we are interested to see the free electrons only, so let us assume there are free electrons, and if I indicate any energy level here, so you see the energy levels are like this. So if this side of the electron is free, it will have on this level, but if the same electron here is free, will find it lower somewhere here or here. So it will be like this. Okay, then one more information could be fetched for the Fermi level, all because the gap anywhere is maintained. This gap is maintained. It indicates that everywhere within the material the concentration is same, doping concentration is same, or it is uniformly doped. So somewhere in the statement it is definitely told to us that it is uniformly doped, or the final electron concentration is uniform. Even if it is not given, we always assume that an n-type semiconductor, given n-type or p-type semiconductor, is uniformly doped. So everywhere the concentration throughout the volume is uniform at every corner. If it is the case, then EC minus EF difference or EF minus EFI difference has to be same in order to have equal concentration, because we know the formula to get N here. So if we try to get N here, or if we try to get N here, we should have same EC minus EF or EF minus EFI. So everything or all the energy levels should be in parallel in this sense. So therefore this is a wrong option, because here it shows that the Fermi level has gone further up, or the difference between EC and EF, EC minus EF, is low. So it tells that there are more number of electrons at this corner, and here it is the difference is large, so less number of electrons at this corner, but the electron concentration is uniform throughout. The only difference is that potential varies from here to here. So the side where potential is positive, the electrons will find it a favorable case, their energy will be reduced, and wherever they find negative, their energy will be increased, or the total kinetic energy, the difference above the EC, the distance above EC, kinetic energy will increase. So therefore the D option is correct. Okay, so the next problem is on diffusion concept, and it becomes very clear from the statement that electron concentration in a uniformly doped n-type silicon at some room temperature varies linearly from this value at this distance to this value at this distance. So the concentration is this at this position. It basically drops when we move from x is equals to 0 to x is equals to 2. So if we make a picture of this, okay, let me complete it first. The electrons are supplied to maintain this electron concentration, okay, with respect to time, and the diffusivity constant or electron diffusion constant is also given. When no electric field is present, then find the current density in plus x direction. Now there is a hint that this is from the diffusion concept, all because the diffusion constant is given. So the trick that we can identify quickly that we have to something use about diffusion constant, the silly trick. But the main thing is the current density still exists even if there is no electric field can only happen in the diffusion phenomena. Drift phenomena always demands an external force or external electric field, but diffusion phenomena is internal process, or it only requires the concentration gradient, but in order to maintain it we need a constant supply from somewhere. So that has been told us to don't worry about that. There is a constant supply of excess electron at this end, so that they diffuse and they are decreased at this side. So when they diffuse, the amount doesn't decrease at this end, means at this end, there are more number of electrons, 10 to the power 17 per centimeter cube, and here they are 6 into 10 to the power 16, or if I make the onto the x-axis, so it is like this. This value is this, and this value is 6 into 10 to the power 16 per centimeter cube, and this is x is equals to 0, this is x is equals to 2 micron. So it drops like this, and all because we know whenever this diffusion process, because of this excess carriers here and less number of, there will be a diffusion process. So electrons are more in number here, so this is the excess amount, and due to this excess amount there will be a diffusion process to this side, so electrons will move to this side, because this is the electron concentration which is given to us, because this is the n-type material. Okay, and in n-type material this scenario might be developed for holes as well, but it is properly said the scenario is for electron. Okay, then if electron moves here, then the final current has to be established in this direction. So there are more number of electrons at x is equals to 0, there are less number of electrons at x is equals to 2 microns, so the final current density comes in this direction, which is in the opposite direction. So J diffusion, all due to electron, is dnq dn by dx. dn by dx, if there is a curve, irregular curve, not a linear curve, and at some point we have to find slope, then we utilize this. Otherwise, if it's a linear curve, we can say that dn by dx is same as delta n by delta x. So dnq n1 minus n2, or let me call it n2 minus n1, x2 minus x1 in positive x direction. So this is x1 in positive x direction, this is x2, so this is n1, this is n2. So if I keep this thing here, so it is dn into q, and this is j ultimately in minus x direction. In minus x direction, it is dn is given 35 centimeter square per second, into q is 1.6 into 10 to the power minus 19 into this bracket n2 minus n1. Now this n2 is this, minus n1. n1 is 10 to the power 17 upon x2 minus x1, 2 micron minus 0. So here it is 2 minus 0 is in micron, we have to convert it into the centimeters, so this will be minus 4, everything will be in this. So therefore this gives me, and here comes the negative sign, all because this is a small number, this is a big number, which confirms that this is in opposition to the direction which we have assumed. We have assumed a positive direction, this. So this confirms negatives with the negative sign. So either we indicate minus sign here and then say in the same x direction, or if we already discussed theoretically that is it in minus x, and then we can skip the minus sign. So I'll in general remain it with j, and let the minus sign comes for identification that this is in the reverse direction somewhere in the minus x. So it is 35 into 1.6 into 10 to the power minus 19 into this minus this will be 10 to the power 7, or minus sign will come here outside, then 10 to the power 17 minus this. So this is 10 minus 6 is 4 into 10 to the power 16 upon 2 into 10 to the power minus 4. So if I calculate it, it comes 1120 ampere per centimeter square with negative sign. So please mind it, the negative sign indicates that this is in the opposite direction to the convention we have made. We have made a positive convention of x in this direction. So we are expecting some current here, but if we are getting a negative sign, is an indication that the electron current is in the opposite direction to the electronic flow. Okay. So this question is based on the concept of drift that we can conclude from the statement. This is the scenario in an n-type silicon of the length 1 centimeter and some uniform cross-sectional area, biased with this 10 volts plus here minus here, and the doping concentration is 10 to the power 16 with the electron mobility this. Find the average time in microsecond taken by electron to move from one end to other. So definitely if we see the electrons, it is, this side is plus and minus as per the polarity, and 10 volts has been applied. So electrons are definitely moving from this end to this end, because there will be an electric field like this. So any hole will move like this and the electron will move like this. But the direction has not been asked, so that hardly matters here. So if we move further, in order to cover this, or in order to simply get the time, we can say that the time for any distance L measurement, so it is length upon velocity. So total length which it has to cover is 1 centimeter, and we should have some average velocity in between, which is nothing but the drift velocity, because we know drift velocity is statistically average value, statistical average, or in symbol mean of all the lots of carriers. So the drift velocity will definitely come all because of the applied electric field here, mu n, and this drift velocity, electrons are moving because it is full of electrons here, majority carriers. So therefore this is the formula of drift velocity, where it is mu n into electric field. Electric field has not been provided directly here, it is being discussed in the terms of voltage difference. So this minus this, so the voltage difference is V, and it is spread across length of L 1 centimeter, so it is V by L. And we have already seen this case that a uniformly doped extrinsic semiconductor is having a sustained electric field. Electric field is maintained everywhere. So this is a constant electric field. We should not think that electric field will be more here, less here, less here. It will be almost maintained because of the assumption that the concentration or electron concentration is uniform. So the charge concentration remains uniform throughout. If it remains uniform throughout, we expect a sustained electric field due to this potential difference of 10 volts. So therefore the electric field comes as mu n V by L, and we can directly keep it here. So if I again come back to the time calculation, 1 centimeter upon the average velocity, which is mu n into E. Mu n into E is V by L, so it is V by L, and this is L length is again 1 centimeter. Earlier also this was length, so it goes to 1 centimeter square upon volts is the voltage difference, so that is mu n into 10 volts. Mu n is given as 1000 centimeter square per volt second into 10 volts. This volt and volt unit will go away, centimeter square and centimeter square will go away, so it will be seconds only. So this will be 1 upon 1000 seconds. and 10 to the power minus 3 seconds. So it is 1 millisecond or it is 10 to the power 3 microsecond. So in microsecond it is 1000 because we have had to tell in the microsecond. So this is the procedure. Okay, so here's a good one. In a semiconductor, the energy band diagram profile has been plotted like this. So the energy band diagram is reducing linearly in this direction with the slope minus 0.1 electron volt per centimeter, and it is confirmed with minus that in the x direction, from x is equals to 0 to the positive x direction, the slope is negative, means it decreases. Okay. Also the electron profile, the electron concentration or electron density profile is also given, where electron density is mathematically given as this, which is e to the power something positive with respect to x. That means we can expect some increase, though it is not linear, it is exponential, but approximately, it has been shown approximately linear, but we'll go by mathematics and we'll take it exponential only. Alpha constant is given, other constants kT by Q is given, diffusion constant is given, and we have to find the total current density or current density in ampere per centimeter square at x is equals to 0. Okay, means this thing is everywhere, but at this point, so it is not like this process stops here or this process stops here, it is continued here and we have to find at this point. So first of all we'll try to write J and due to n, because everything is for electron here. So it is J drift n plus J diffusion n, and let us try to find drift and diffusion separately. Now because concentration gradient has been given here, or there is a difference in concentration here, so the diffusion part, this chart is helpful for diffusion process. We'll make use of this graph, and in this graph you see, because the band diagram changes, and band diagram or energy level, any energy level shows the electron's energy in the energy band diagram, and if it is going like this linearly, then we have seen already in the previous numerical, in some previous numerical, that if the whole band diagram is that remains parallel but reduces, that means there is an electric field applied. So this side of electrons are lowering their energy, this side of electrons are getting higher energy. That means the electron's energy could be lowered by providing a positive potential, or the energy of electrons can be increased by giving them negative potential so that they are further agitated. So this side is definitely negative and this side is definitely positive, not here, in fact somewhere here, right? So there is an electric field, definitely there is an electric field like this. So there is a sense of electric field, and here if you see, electrons are increasing in numbers into the plus side, so there definitely electrons will flow in this direction, and definitely the J diffusion will happen in this direction. So less number of electrons in this region, more number of electrons in this region, so definitely there will be J diffusion in this direction, and all because electric field is in this direction, so the electron current, the electron will be pushed in this direction, so the electron current will definitely be in this direction. So J drift. So the electron's energy has been lowered, so positive to negative, so there must be an electric field, and the slope is nothing but the electric field. If you see, this is energy per this, and we have seen electron volts corresponds to a thermal voltage of same value if we skip it with this. So the from this diagram, the electric field is, or the corresponding delta V per centimeter is this divided by Q, or Q will cancel E, so it will become minus 0.1 by. Okay, so that means the potential difference per unit length is nothing but the electric field. So minus, that indicates that electric field in this direction. So minus value means in the x direction it is minus, that means it is in this direction. So if electric field is in this direction, so the holes will definitely move to this direction, and therefore the electrons will move to this plus x direction, and therefore the Okay, I'm sorry. If hole moves in this direction, so the current density, I'm sorry, will definitely be in this direction. Okay. J drift, because even if the electrons are moving in this direction, due to the electric field, the electrons move in this direction, but the current contributed by them, or the current contribution, will definitely be in the opposite direction of electron. So I'll correct myself. The drift. So we have seen the idea of drift and diffusion. So let us consider one by one. Drift is simple, so we can quickly go for drift. J drift. The direction consideration has already been taken care of, so we'll not indulge into the direction or plus or minus. We separately know it. Otherwise, if we did not calculate this, then we would have gone for an exact polarity interpretation here. But now we can escape, because we have interpreted that this is the direction of current. So J drift is sigma into E, sigma n into E, and all because it is sigma is the conductivity, nq mu n, nq mu n E. Okay. So this is the conductivity into E. Now electric field has been calculated. This is this. Now we need not to have minus sign here, because we have already seen electric field is this direction. And what about n? Electron concentration, it is not fixed, it is being given like this profile. So this value is n at 0. And why we need n at 0, x is equals to 0? Because the current density has been asked at x is equals to 0. So we have to calculate J drift, and everything is a function of x, so we have to calculate at x is equals to 0 everything. So J drift is basically a function of x here, because the concentration is not fixed here. So let me write it properly. It is nx into q mu n into E, and then we'll keep it x is equals to 0. So the concentration at x is equals to 0 will become, if we keep here x is equals to 0, makes this whole thing 1, and then it only remains with 10 to the power 15. So n0 is 10 to the power 15 per centimeter cube. So that thing comes from here, 10 to the power 15 into q is 1.6 into 10 to the power minus 19 into mu n. Mobility is not being given. So interesting. In any standard competitive exams problem, if some data is required, it is definitely given to you at some proper examination. Otherwise, you need to have your memorable data. But in GATE, definitely, if anything, even if Q is required, the electronic charge, they will definitely provide 1.6 into 10 to the power minus 19. I do not write it all because it is not of the concept part. But here mu n is not separately given. So therefore there must be some idea, some trick. dn is given, and we know that dn by mu n is Vt or Kt by Q, and Kt by Q here is being given as this value. So mu n is dn upon Kt by Q. So dn upon Kt by Q we can write mu n is dn upon Kt by Q, and Kt by Q value is 0.026, and this is electron volts if it is energy, otherwise we can only read it as volts for the voltage purposes. 0.026. So dn upon Kt by Q upon Vt. So dn upon Vt, thermal voltage, is nothing but mobility. So that also we have written here. And dn value we can keep in the next step. Into electric field we have calculated as 0.1 volts per centimeter. So it is 0.1. Now we can keep dn also. So dn is given as 36. Okay. So now if we calculate, we expect, because everything has been kept in centimeter units, so we expect ampere per centimeter square. So if we solve it, this comes as 2.215 into 10 to the power minus 2 ampere per centimeter square. Okay. So this is the J drift, and all because it is in minus direction. So if we have kept everything in the proper sign, like E here will be negative, so minus will come here, which will indicate that this is against our positive convention of this side. So we are assuming a positive X this side, so minus n indicates it is this side. So either you analytically say that it is this side, then we need not to show minus. So otherwise, if I in general write J drift X at X is equals to 0 is this. So okay, then I need to find J diffusion N is dnq dn by dx. Again, this is a function of x, so at x is equals to 0, at x is equals to 0. So first of all, I need to find dnq into dn by dx. Now n is this, so dn by dx, I'm writing it here only, dn. So if I differentiate it, this gives me dn by dx as this whole power will come down, and this q I can take down as q, so it becomes kt by q, which is a value 0.026. So it is 10 to the power 15 into alpha x, oh sorry, with respect to x only I am differentiating, so alpha upon kt by q upon kt by q into e to the power this whole thing into x. But because we are finding it at x is equals to 0 here, so this slope actually we are finding, so at x is equals to 0, this thing at x is equals to 0 becomes 1. E to the power anything coefficient into 0 is e to the power 0 is 1. So we only need to find this is the value at x is equals to 0, and this is very simple. This is 10 to the power 15 into alpha is given as 0.1 upon kt by q. Kt by q value is 0.026. So this is dn by dx at x is equals to 0. Then only this exponential term after taking derivative becomes 1. Okay, so in this dnq into dn by dx has been calculated, 10 to the power 15, and one more makes one minus makes it 10 to the power 14 upon 0.026. So this thing at x is equals to 0 effect has been taken care of, so we need not to show it again, and this will be dn is okay 36 into q is 1.6 into 10 to the power minus 19 into 10 to the power 14 upon 0.026. Okay, so this whole thing, and nowhere the minus sign comes, and that is logically correct also, because the final diffusion current due to electron, because electrons are traveling here, so the current would be in this direction, and it is in coordination with the, in synchronism with the positive x convention, so therefore no negative sign should come anywhere, and it indicates that it is in positive x direction. So if I calculate it, it comes as, okay, great. So fortunately this also comes as 2.215 into 10 to the power minus 2 ampere per centimeter square. Interesting. You see this much current due to diffusion. So in this, what has happened finally? The J diffusion is same as J drift. J drift was this, J diffusion is this. Both values are exactly same, but unfortunately this is, if we add these two, the resultant will be 0, because the direction of both is opposite. J diffusion is in this direction and J drift is in this direction. So therefore if we add these two, the total J is this value plus this value is 0. So it becomes 0 perfectly. So the whole drift effect has been cancelled by the diffusion effect. So both things are, but most of the time they are in support also. Otherwise, in some practical situation, this may also happen. So this is the answer. So here the next problem is also interesting. An N-type silicon is uniformly illuminated or radiated with some light intensity, and the doping concentration is this. That means it is N-type, obviously. And due to this uniform illumination everywhere, so there is a throughout optical generation, excess carriers are generated, and the generation rate is this throughout because everywhere there is uniform illumination. We are not locally radiating any piece. So everywhere the generation rate is this. Now when radiation is turned off suddenly at t is equals to 0, then we have to calculate the holes concentration at t is equals to 0 and t is equals to this. So we know that in any extrinsic material, if there is an external energy imparted like radiation or illumination, then the majority and minority carrier concentration goes up. But majority carrier concentration is already so high so that the excess amounts are neglected in front of that already existing amount of this. It's a high doping. But the minority carrier concentration are already very poor, very less. So anything in excess to that is significant. So we only talk about the excess minority carriers, and therefore the question also asks about the minority carrier concentration. So we know the profile that at this time t is equals to 0, if illumination is stopped, then let's say this is the steady state concentration. At this, let's say this much is the excess minority carriers. So let's say this is Pn at t tends to infinity, we call it Pn naught. Holes in N type of semiconductor. So Pn at t tends to infinity means in steady state. So as soon as we just stop the radiation, just turn off the radiation, then excess carriers will try to diffuse as time progresses, and the excess carriers will finally, they all will be removed off due to recombination. So as they will try to diffuse like exponentially like this. So here where they start from, we call it Pn at t is equals to 0, and we symbolize it with Pn0 symbol. And then we are interested to determine Pn at a general time t. We know that this profile is where we finally go Pn naught steady state value plus the difference where we start from delta p, that means the excess carriers e to the power minus t by tau p, the lifetime carrier lifetime of those carriers which are under observation, under consideration. So the holes. Now delta p is definitely also, okay, let me write one more step. Delta p is Pn0 minus Pn naught. So this value is Pn naught. So Pn0 minus Pn naught into e to the power minus t by tau p. Now because the low level injection is also mentioned, so that means the minority carrier concentration in steady state could be assumed as 0. So it's a very high doping concentration, so therefore the minority carrier concentration, so low level injection for the holes concentration, that means their steady state concentration is very poor. So approximately we can have this thing as approximately 0. So that is the intention of this statement. So therefore we can approximately say that this is 0 plus Pn0 e to the power, because Pn naught is again 0, so this becomes this much into e to the power minus t by tau p. So this is what the equation which we are trying to get. Once this is known, we can get this, and we can get value anywhere at t is equals to, let's say, 0.3 microsecond. So this value or this value can be obtained, but in order to get this equation, we will have to have this value. So okay, one more information we have, that once we try to draw the slope at the initial value, so the initial rate of recombination, the slope at t is equals to 0 is the initial recombination rate, because just the generation, the radiations have been stopped. So far everything was in steady state, in earlier steady state. So at this time it was same as Gn, the generation rate here at t is equals to 0. So the slope, you know, where it meets is, this distance is tau p, and we know that excess minority carriers, that means pn0 minus pn0 upon tau p. So this divided by this is the slope, initial slope, and initial slope from the prior steady state condition is same as recombination rate at t is equals to 0, and this is same as generation rate at t is equals to 0, that has been given as this. So therefore now we are done. This we can approximate as 0 under low level injection of holes. So therefore pn0, where we have to start from, upon tau p is approximately Gn, is being given as 1.5 into 10 to the power 20 per centimeter cube per second. So therefore pn0 is nothing but pn at t is equals to 0. This is the first question which has been asked. So at t is equals to 0, it comes directly as tau p into Gn, sorry, not Gn, Gp everyone, I'm sorry, extremely sorry for this, because here holes are under consideration, so the convention should be for un and up. Initial recombination rate is same as initial, the generation rate up to the steady state. After that there comes the transient state, and after long time there again comes the steady state. Tau p Gp. So this is therefore tau p is being given as 0.1 microsecond is this, into Gp is 1.5 into 10 to the power 20. So this gives me approximately pn0, and that is 1.5 into 10 to the power 13 per centimeter cube. So this is the first answer. For the second answer, because there we start from, so we need to have this thing, but in order to get this value at t is equals to any other value, any other time, we need to have this equation. So the equation is now pnt is equals to pn0. pn0 is this value, 1.5 into 10 to the power 13 per centimeter cube into e to the power minus t by tau p. Minus t by tau p is 0.1 microsecond, and we have to calculate this thing at pn at t is equals to 0.3 microsecond. So it becomes 1.5 into 10 to the power 13 into e to the power minus 0.1 microsecond. 0.1 microsecond. Oh sorry, we have to calculate at t is equals to 0.3 microsecond, and the tau p is 0.1 microsecond. So microsecond will get cancelled, and this data comes as 7.47 into 10 to the power 11 per centimeter cube. So this is the answer for t is equals to 0.3. As we expect, it falls. So we expect that the holes concentration or excess minority carriers will drop down. Finally, they will come at rest, the steady state value pn naught. But pn naught here we have expected or we have assumed as 0. So this is the second answer. Okay, so here's the short but tricky problem. That is the doping profile or doping distribution, almost linear it seems, in a p-type semiconductor. So from 10 to the power 14 to 16, if I go, that may not be linear definitely, because it's wide change, a very exponential rise, but that is on to the log scale, means we can find the corresponding log value of it. So that we'll be finding. So it is given in the log scale. We have to find the magnitude of electric field in kilovolts per centimeter due to non-uniform doping. because here the doping concentration is high, here the doping concentration is small, and due to that there will be an electric field. Why there will be an electric field? If we leave the material as it is, and if there is no electric field, then the larger concentration here will diffuse out to this side, and then after some time there will be some uniform doping concentration or some uniform final concentration. But because this situation is maintained, all because there is a drift current also. So without that this situation cannot be maintained, and if this situation of non-uniform doping is maintained, then there must be an electric field. More number of Na, it is the acceptor impurity, so more number of holes here, less number of holes here. There must be an electric field from more number of holes to less number of holes, like this. But because we are not interested in the direction, it is only important to calculate the magnitude. So we start arguing that J total must be 0 in the steady state, and that only can happen when J total, which is J diffusion plus J drift, so both are same and opposite, then only it can happen. So that means J diffusion is minus of J drift. Okay, so I have to utilize this. So it's logical also, because in order to maintain this scenario we have to supply some holes from here, which ascertain that there must be some condition like this, that there is a drift also and there is a diffusion also, like this. So when this happens, J diffusion, I'll write it here, diffusion is Q dP minus Q dP dP by dx is equals to J drift is sigma PE. We are considering holes because Na is given us in the P type, so that's what we are considering. Now I'll write it here. Q, we are only interested in the magnitude, so it is Q dP dP by dx is equals to QPN PQ mu PE, and we know that Q and Q gets cancelled, and dP by mu P dP by dx is equals to P into E. P is obviously approximately so this thing becomes Na comes here 1 upon Na. P is also Na, so dNA by dx is E, or this I can write as d by dx of some logarithmic function of Na as x is equals to E, because then only it will be 1 upon Na dNA by dx. So this we know that it is could be written as log Na 1 at x is equals to 1 minus, or this minus this, let me do it, 2 minus log Na at x is equals to 2 upon delta log of this upon delta x, 2 micron minus 1 micron, so it is 10 to the power minus 4 for centimeter, because we have to calculate anything in the centimeter. So okay is equals to E, so that's what we have to calculate. Electric field we had to calculate, so that's what we will be getting here. So this is the value of electric field. Now log of Na of this value, so if I take log of 10 to the power, this is x is equals to 2 to the power 16 minus log of 10 to the power 14 upon 2 minus 1, that is 1 into 10 to the power minus 4 centimeters. So that I must get as 16 minus 14 upon 10 to the power minus 4 volts per centimeter, and this is 2 and this comes up 20 kilovolts per centimeter. So this is the answer. This comes up and makes it 20. So the answer is 20 kilovolts per centimeter.